All right, so now we're going to talk about electric potential energy and a new concept, the electric potential. So let's start with a question. Suppose I have a proton and an electron, and they're fixed and held apart at a distance of 1 meter. So here they are in this picture. And then what I do is, while keeping the proton fixed, I let go of the electron. And what's going to happen? Well, it's going to, of course, get attracted and move towards the proton. And so the question is, as the electron approaches the proton, what happens to the force the electron feels? Think about this, and we'll talk about it in a second. Okay, hopefully you got that. It gets bigger. If we look at our magnitude of the electric force equation, something kind of like this here. So the two charges are staying the same. It's the charge of the proton and the electron. The only thing that's changing is the distance of separation, r. r is getting smaller. And so as r gets smaller, overall, since it's in the denominator, overall this will increase. We'll find that when you're dealing with these charges, if they move, the force is almost always going to change. And so that causes us a problem. And so here, as the electron approaches the proton, now if we want to sort of try to describe this motion in terms of forces, typically what we would do is you take F equals ma, and then we'd solve for the acceleration. So I say acceleration equals F divided by m, and then we'd try to take that and plug into one of our equations, our kinematics equations. However, if you remember, these equations are only good if the acceleration is constant. Well, right here, if the force is changing, the acceleration is going to be changing. And so even though with electricity, it's really nice to think about a lot of things in terms of forces, it can be limiting if we're trying to describe the motion. And here, if we wanted to actually solve for things like the velocity of this electron or where it might be at some certain time, we'd have to use some nasty calculus. And so let's see if there's another way to think about that. And that way is going to be thinking about it in terms of energy. So the electrostatic force is a conservative force. You remember that those are really special. We basically learned two of them at this point, the elastic force, like a spring, and then gravity. And so the electrostatic force is a new one, and this is a very nice kind of force to deal with, the conservative force. It can be really helpful in solving different kinds of problems. And so we're going to try to define a new potential energy that we'll call the electrostatic potential energy. And so let's kind of look at this, a little example. So here's something we might have seen in mechanics. Suppose you have some building and you lift some ball up to the 4th story of the building. What happens to the ball's potential energy? Well, hopefully you agree that it would increase if we did this. Well, we can do the same thing thinking in terms of the electric field. And so here, a real handy picture that we're going to use, we're going to talk about this a lot, is the electric field of a capacitor. So the electric field of a capacitor is constant, and so it's very similar to that of the gravitational field at the surface of the Earth. And so we can use these analogies to help us think about this, because one problem with these electric potential energy and the electric potential is that it can be really hard to visualize. And so here, if I lift this ball up to the 4th story of the building, I increase its potential energy. Well, by the same token, if I take this positive charge here and take it from the negative end to the positive end, I've increased its potential energy as well, right? Because it doesn't want to be over here next to these positives. It wants to be over here next to these negatives. And so if I let it go, it's going to cruise down that way. So I've increased its potential energy by moving it there in a very similar fashion to how we would have done it with the gravitational energy. Recall how work operates. We have an equation kind of like this, where this is the dot product, if you think about it that way, between F and D. And so if we draw this, this is the force, and this is the distance, and the way this is defined is that angle is the angle in between. And so a couple of rules about force, or about work rather. It's positive if the force is in the direction moved. So if the force is sort of helping the motion, it's positive work. It's negative if the force is opposite the direction of motion. And it's zero in cases like, for instance, like a normal force, where the force is perpendicular to the direction moved. Conservative forces, which again, the electrostatic force is, work this way here. And so there's this nice little rule, so because sometimes you'll be asked about the work or the potential energy. So the work done by the electric force is always going to equal the negative of the change of the potential energy. This is the same thing as this one. I just swung the negative sign over here. And so we'll use this in looking at different situations. So here's a situation, again with this capacitor and a charge in the capacitor's field. It's a constant E field. What happens to a positively charged ball's potential energy if it moves down? So if we move this ball down, or this charge down, what happens to its potential energy? Think about this and let us know. All right. Hopefully you got that it decreases. The positive charge, again, wants to be away from these positives and towards these negatives. And so if it goes down like that, it's going to lose potential energy. So its potential energy, in this case, would be negative. It would be decreasing. And so similar, the same situation, this positive charge ball moves down. What does the electric force do? Does it do positive work, zero work, or negative work? What do you think? Okay, hopefully you got that it does positive work. Now we can think about that a couple different ways, but the easiest way here is that as this charge goes down, the electric field is pushing downwards. And so the force on this guy is going to be Q times E. And so since the force, or the charge rather, is a positive force, the force that we feel here, this charge is going to feel is downward. So the force is in the same direction of motion, so it's positive work. Another way to think about it is we can use this little handy rule about conservative forces. And so since delta U, the potential is decreasing, that's negative. So that's a negative, and then a negative is a positive. So electric field here does positive work. Now one thing that's tricky is that we're doing this for a positive charge. You can also do it for a negative charge, and sort of the opposite things are going to happen. So you got to be careful. We'll talk much more about this. So electric potential is a convenient way to work with this energy. And what we're doing is we're basically saying that it's the electrostatic potential energy per unit charge. And it's called the electric potential. We use a V. The units of this are volts. And so this is where volts comes from. Now you can do this in the case where, so the potential is basically, electric potential is the electric potential energy divided by charge. Now oftentimes we're going to be dealing with changes in this, and so we'll oftentimes talk about delta V as opposed to just V. And again, the units are V, which are volts. And so we can set up the same example here. The electric potential at point A is blank that at point B. So pause and think about this, and we'll get back. So in this case, the answer is greater than. The electric potential at point A is greater than that at point B. And the way we can think about this is we just developed this equation that says basically potential equals the potential energy divided by charge. So for a positive charge, we just sort of talked about that up here, okay, you're going to have a higher potential energy than down here. And so since it's a positive charge, this Q is positive, and so if the potential energy is higher, the potential has to be higher. So electric potential, you can think about our equation looking like this here. If we swing it around and solve for the potential energy difference, so we just sort of defined just a second ago, we said that delta V equals delta U over Q. And so now I can solve it this way here, where delta V, of course, is the change in the potential. Now we can compare this with one of our equations from mechanics. Okay, the change in the potential for gravitational potential energy. And so here you've got mg times the change in the height. And so we're going to find a lot of analogies between the electric potential and height. And so that can be really helpful because, again, electric potential is something that's very hard to visualize, but with the height, hopefully that can be helpful. And so if we go back to our pictures of the building, we can set up what's called equipotential lines, which what that just really means is it's lines where the potential is constant all over the line. And so for a building, that would just be the floors of the building, perhaps 10, 20, 30, 40 meters or whatever. Well, the same thing we can set up with our little capacitor field. So we can set up a little field where you can make them up 10 volts, 20 volts, 30 volts, 40, so on and so forth. But the height increases as you get closer to the positive, just like we sort of just developed. So if you're a positive charge up here, okay, you're at a high electric potential. which means your potential energy is higher than it would be over here at one of the lower points. And so basically positive charge behaves like a mass would in the gravitational potential energy. That can be helpful for us in trying to sort of develop these analogies a little bit further, which we'll do a lot of. All right, let's try an example. This is an old exam test question. If an electron is accelerated from rest through a potential difference of 300 volts, what will its speed be? We're given some choices. Now, on a problem like this, the idea here is that the only force acting is the electric force, which is a conservative force, so we can use conservation of mechanical energy. Now, in a problem like this, the tricky part is to figure out what is the potential initial and what is the potential final. And so our term for the potential energy, U, is Q times V. We want to know is which V is which. And so what can be helpful is this picture again from the capacitor. So we sort of change this around to sort of works for our potential problem here. And so one end, so this electron is accelerated through a potential difference of 300, which means it's sort of let go from one of the two sides here. Well, which side would it be let go? Well, if I'm a negative charge, I would be let go of here. If I'm let go down here, I want to get away from these negatives and towards these positives. And so the electron, its initial potential would be 0, and its final potential would be 300. And also just remember that potential is very much like height. We can sort of set the 0 to be wherever we want. So I set 0 here. I didn't have to, but it just makes life much easier. And so sort of a rule of thumb here that the positive charge will feel a force in the direction from high to low potential. So the positive charge, as we discussed before, if it's let go, it wants to start, if it's up here at the top, it wants to get away from the positives and go down. It wants to go to a lower potential. The electron, if you let go, it wants to go to a higher potential. So that can sort of help us figure out which one is which. So in this problem, we want to get an equation kind of like this. This is just our conservation of mechanical energy. So the final mechanical energy equals the initial. Initially, there is no kinetic energy, so that's nice. So that the answer does come out to be D here. And what we can do is just kind of go through this. So K final is going to equal Q VI minus Q VF. And then I can pull the Q out to get VI minus VF. And if I set this equal to the fact that it's the final kinetic energy, 1/2 m velocity squared equals Q VI minus VF. And then here what I do is I go through and just solve for my velocity. So it'll be 2Q VI minus VF over m square rooted. Now the thing here is you can kind of check to make sure you got everything right. This term in here should be positive, right? Because you can't take the square root of a negative number. And so the Q times VI minus V final should be a positive number. And so what is, well, Q for us is negative 1.6 times 10 to the negative 19 coulombs, and then we're multiplying that by VI minus V final. And remember, we said the VI was, excuse me, 0 volts, and the V final was 300. So this is going to be 0 V minus 300 V. This will be a negative number, so overall this term will be positive. So that does agree with what we expect. And again, when I did the numbers, I got 1.0 times 10 to the 7th. So the last thing we want to mention is the electric potential due to a point charge. So far we've talked about the potential in more generic terms. We can also calculate the potential from different distributions of charges, and here's the one we can do from a point charge. So this equation is real similar to equations we've used for, say, the force and the electric field. And I gotta be careful though, this is a scalar. So this is actually easier to calculate. There is no direction to this. It's just a number. The potential is just a number, kind of like height. There's no direction to it. And so we can use this to calculate the potential in different kinds of things. So an example would be something like this. So this is a problem that's just like sort of the start of this little lecture. So we've got a negative charge and a positive charge. Here they're held 2 meters apart. And the size of the charge is 1 times 10 to the negative 6 is the negative, and 2 times 10 to the negative 6 is the positive. And they're held in place, and we let go of the negative one. And we want to know is what happens to this as it travels from 2 meters away to 1 meter away. Now again, to do this with forces is very tricky, but to do this with energy, it's not so bad. When I do this, this is again an old test question, I got 8.8 centimeters per second. And so let's look at this here. So it's the same idea. The only force acting is the electrostatic force, which is a conservative force. And so we can set up our equation here. Now here's a little bit of a new tricky part, is that when there's more than one charge, you got to be careful which one you're talking about. So here, okay, we're talking about the energy in this equation of the negative charge. Okay, we're not talking about the energy of the positive charge. And so the Q we use here will be the Q negative. Now, just like last time, it's a little tricky to find the VI and the V final, but we can do that by using our new equation. And so the thing is the idea that we're having here is that our negative charge is moving in the potential that's caused by the positive charge. So we want to use this positive charge here to find the initial and the final potentials. And so if I do that, again, using my K constant, I get about 9,000 for the initial and 18,000 for the final. And so we go through with our equation. Again, I can say that the initial is non-existent, and it's very similar to our last example. We get down to this point here, again, the same sort of idea. So if you look here, the difference in potentials will be a negative number, and the charge is a negative, so those two cancel to give us what we want, a positive underneath the radical sign. And when I plugged in my numbers, again, remember that this is 1 times 10 to the negative 6 coulombs negative for that charge. I got, again, that number we had of about 8.8 times 10 to the negative 2 meters per second squared.